Hello, I'm Jim Peterson. I'm a professional geologist at Princeton Geoscience. I'm the founder of the company, which was started in 2000.
And I'm Tim Hall. I'm the Vice President for Field Operations, also a professional geologist, and I've been with the company for almost 20 years.
So we're here today in one of the Princeton Geoscience geophysical logging field units to discuss synergistic review of multi-parameter geophysical logs. We're going to use an example from a hole that was logged in the Newark Basin, which is a sedimentary basin, sedimentary rocks ranging in texture from mudstones all the way up to a conglomeratic sandstone. So before we get into that, so what do we mean by synergistic review? It's as simple as multiple lines of evidence, applying multiple lines of evidence concept. Most reviewers, most investigators who've developed a conceptual site model will have applied that. Simply using all of the information at your disposal in combination to get a better understanding. In this case, the focus will be on the geophysical logging data set. And that data set is acquired, it's represented as multiple tracks on a multi-parameter geophysical log. And those tracks result from running a series of different probes down the borehole or well to gauge different characteristics of the borehole and the environment surrounding the borehole.
Yeah, so to look at those logs, here's the log format that we have showing all of the logs together. So from left to right, we have the caliper showing the diameter of the borehole, the natural gamma signature, the single point resistance. And I'll point out here, we have other series of videos showing in detail what these logs actually show. We're just giving an overview here. We have fluid temperature and resistivity. We have the two acoustic logs, acoustic amplitude and travel time. Then we have the optical televiewer. And finally, heat pulse flow meter under ambient and pumped conditions.
Yeah, so as Tim mentioned, it's an overview here. We have be sure to check out the other videos which explain the use of each tool, what it physically looks like, and how it's deployed, and principle of operation. But what we're going to do now is look at the logs one by one, as if you had no knowledge and you gradually ran each log. That's a way to illustrate what you can get from each of the logs. So the first and simplest log is this mechanical caliper, which may know is this thing that runs with 3 arms that just measure the diameter of the borehole. And just looking at this log, you might readily see that it's a 6-inch diameter borehole. Looks to be on gauge with the drill bit for most of the borehole depth, and then it has a number of sharp deflections, which one might reasonably interpret to be fractures. You get some roughness on the borehole, some just overall roughness. One might gather from that, it's maybe a softer rock in some zones, and then it's a cleaner, smoother line elsewhere. That might be harder rock. Next is the natural gamma log, which some people think of it, and in some situations it's warranted to think of it as a shale log or a clay log, something showing more or less radioactive rock, being higher radioactivity, generally indicating shales or muds. And in this case, looking at the character of that log, you would see a lot of variation, going from well under 100 down to say 50 counts per second, up to 175 or 150 or so, well over 100. You might very well conclude from this that you have rocks that range from mudstones all the way up to sandstones, with the initial knowledge that you're in a sedimentary basin. Another thing you might take from that is to notice that some of these fractures seem to correspond to areas where there are major inflections or changes in bedding, changes in rock type, going from, say, a mudstone here into a more sandstone dominated situation here. It's pretty common to have that at areas where you have weaknesses between different lithologies for there to be bedding parallel fractures. So you might think of some of these as bedding fractures. So adding on the single point resistance, which is the simplest electrical log, it's also a good one for finding bed boundaries. Frequently, the single point resistance log will show as a reciprocal of the gamma log. So you have a low gamma response and a high single point resistance. And that is an indicator. The gamma log on its own, you can think of perhaps maybe as a shale indicator, mudstone indicator. But there are exceptions to that, where you can have high gamma in a coarser grained rock if you have certain mineralogy of making up the sands. So, but when you have another log to compare, in this case, a low gamma makes you suspect sand, and a high single point resistance means it's resistive, electrically resistive, as we know that sands are and shales are not. That's a second line of evidence to make you think that this is a sand body, a bed of sand. Likewise, all these others that go in the same way, and in the opposite, that this would be a shale or mudstone interval. Next log that's we can consider is the fluid logs. They measure the temperature and the resistivity of the fluid in the borehole. The fluid in the borehole is not directly necessarily a measure of the fluid in the formation adjacent to the borehole. Quite commonly in long vertical open holes, there are different hydraulic heads in the fractures at various depths, which sets up a condition where when you drill the hole through that, you have the opportunity for there to be vertical flow into the well, up or down the well, and then out of the well. And so what it results in is a column of water between two fractures that have flow that has common characteristics, has the same characteristic, fluid temperature and fluid resistivity, for example. And then so someone looking at this borehole log might see that there's a fracture here. It corresponds pretty closely with this inflection in the fluid resistivity. They might see here at the bottom, and it's rather uniform all the way down. It doesn't change. There's another fracture at the base, and there's a change at that fracture. So what you probably one would conclude if they knew nothing else from here is that there is probably some vertical fluid exchange between this upper inferred fracture and this lower inferred fracture. I say inferred, so we haven't seen the fracture. We don't know it for sure. In the old days, these were the only logs that were existent, and you'd pretty much make a conclusion of a fracture. We have other logs now, these image logs that Tim will pop up, which make it possible to use visual observation of images of the borehole wall to see those fractures, and as we'll show with a separate set of logs, to figure out the orientations of those fractures. In this case, we have two logs from the acoustic televiewer. One is the amplitude, which is the energy scattered back that's shot out from it, and it's diminished where you have evidence of either softer rock or rough rock, like a fracture, and that is shown in this case by darker lines. And then the travel time, as we've discussed on other videos, how long it takes the acoustic impulse to come back to the probe, the centralized probe. And so generally, where you have fractures, you're expecting to see a lighter tone. It's plotted as a lighter tone here, indicating enlargement of the borehole. Features like these low dark traces that have corresponding lighter traces on the travel time are interpreted generally as fractures. We have we'll show on the other with the other log, we're much more zoomed in and able to look at it in a lot more closely. But just intuitively, people can look at some of these features, and say, yeah, that looks like a fracture, even on this composite scale log. So what do we get from this? We get that sure looks like this banding sure seems to represent different lithologies, coincident with this situation here. This high resistivity, low gamma zone corresponds to this light colored area that seems granular at this magnification. Tim will show you that later. It's that sure looks like a sand, and it is. And these mudstones look like, if you know the Newark Basin rocks, or if you look at them more closely, as we will, that's a mudstone. It's a less bedded mudstone. And then sort of the final thing, before we made inferences about there being flow based on these fluid temperature and fluid resistivity logs, and the fact that the anomalies in those logs corresponded to inferred fractures, which we, upon looking at the image logs, can confirm, yes, those are in fact fractures, and they're bedding fractures. But we don't know which direction the flow was going in the borehole. Whereas with the heat pulse flow meter log, It measures directly the vertical flow, magnitude and direction of any vertical flow within the borehole, down to flows of on the order of about 0.03 of a gallon per minute. And on this plot, we have first a plot of the static flow, which is just what's happening naturally in the borehole under, well, somewhat naturally. The borehole itself isn't natural, but under the prevailing ambient hydraulic gradients, what kind of flow is there going on in the borehole? And in this one, I'm going to let Tim take over and discuss what we see there and wrap it up.
Yeah, so here, as Jim was talking about, the ambient flow we tested first, and that is shown on this blue line here. And at the top of the borehole, we have lower than the detection range of the tool, less than 0.03 GPM of flow. Here we have a little bit of downflow, but really, as we can see, once we pass this fracture here that we can see on the other logs, we have over a gallon a minute of downflow, which is the upper range of the tool. As it is currently designed, we have some other options for measuring higher flows, for quantifying these flows. But we have that same over a gallon a minute of downflow going all the way down the borehole until this fracture here, and we've tested below that fracture, and we get, again, no flow. So we test above and below the fractures to see what change of flow is contributed by those fractures. So then we're pumping, for the pumped heat pulse, we pump at the top of the water column, and at the top we should be getting roughly what our discharge was, which is about a gallon a minute we pump. And here we see that in these upper zone, there's a little bit of flow contributed from this fracture, a little bit from here. But then we see that the pumping of a gallon a minute at the top did not overcome the natural downflow here. So we still have 0.75 of a gallon a minute or so of downflow through that zone. And then again, exiting out here. So that is what our heat pulse flow meter data will show.
So next we would like to discuss the structure log. And what is the structure log? It is the interpreted work of the geophysical log analyst, your geophysical logging contractor, which provides their interpretation of the geologic features in the borehole and their quantified planar orientations. So for bedding, typically, or foliation in metamorphic rocks, and fractures, very importantly. Tim will present that in a minute. But first, I would like to take a look at, to show you the resolution that's available to you. We have right here a structure log for the well we've been discussing. Tim's going to zoom in right now to a 2 or 3 foot section of that log. It's presented, not in the usual format you see it in a report. Obviously, it's 1 foot vertically is pretty close to 1 foot vertically, and it's at a 1-to-1 vertical to horizontal scale here. So there's no distortion. It's pretty much like looking, if you can, except for the sinusoidal aspect of it, it's pretty much like looking at an outcrop. And so, right away you can see things like the changes in lithology. A person could be could be within reason to make the interpretation that this might be a mudstone. You see absolutely no granularity to it, and and you could reasonably also conclude that those are sandstones. We have, just for the fun of it, we have here a Wentworth grain size card, and showing from the very fine all the way up to coarse sands, and you could start to even pick out grain sizes from this. So it's a pretty, high level of high resolution. You can also see, you see the bedding contacts, very clearly here. There's no question about where they are. You have the chance to compare them on other logs with where the gamma contrasts are, for example. You can see bedding surfaces within any one lithology. And of course, you can see fractures. These are some muted fractures here, smaller ones. Tim will show you other examples later. But you can also notice, fractures terminating against, existing in one lithology and terminating against another, as we've alluded to elsewhere. This is a pretty common phenomenon. And also, you see drilling artifacts. Various types are obvious, but in this case, it's the bit scoring as it's pulled out of the borehole and perhaps rotating. So that's just to set the ground. Tim's going to give the rest of the discussion here.
All right, so let's switch back here to the full view of the structure log here. So this is a final structure log showing all of our image logs over here with the sinusoids from north, east, south, west, and back to north. And so here are the sinusoids that the log analyst has picked, looking at the scale, the resolution that Jim showed earlier. So here we can see various features, and we classified them in different using our classification system. So here we have partially open fractures. These are some of those smaller fractures that Jim was pointing out. We have minor open fractures, which are sort of intermediate. We have that high angle fracture that Jim was talking about here that it actually terminates right here, but we showed the whole sinusoid because that is what the software allows. We also have bedding features here shown. We ideally like to pick a range of bedding rather than a singular bedding. If you have a full bed and you can pick if both contacts are along the same orientation, that is the most representative of bedding. Sometimes you just have one contact, so we pick a single contact point for bedding, and often you can see they're right near fractures or are at fractures. We also have, get my mouse over to this screen, scroll down here through various sections of the log. You can see some higher angle fractures through here. And then we are going down to the bottom of the log here, where we can see the red is our major fracture. So this is actually our outflow fracture here. You can see it on the image log. This is where it was over 1 gallon a minute of downflow was exiting the borehole out of that fracture. We can also see the brown are filled fractures. I have some better examples of that further up in the borehole here. You can actually see on the image log, you can see these white traces infill of calcite or gypsum, most likely inside these fractures. So we present them first as the sinusoids themselves that we have picked. We also pick zones of broken or weathering, or if there is some transmissivity provided by Vuggy zones, we will plot those as well. So we can show those both as the sinusoids themselves, then tadpole projections. So these show on a scale from 0 to 90 degrees the magnitude of dip of any of these features, and the direction of the tadpole shows the direction towards which they're dipping. So this is just under 20 degrees, dipping to the west-northwest. Then we have slab core projections, which is basically taking a slice through the middle of the borehole at any orientation you want to show what those features would look like at that slice. So we just have here our standard north to south and east to west cuts. Then we have the actual values. We don't claim that we're actually getting it to the hundredths, where this is what the software allows for ease of display. So here, this would be a feature that's dipping at 11 degrees towards an azimuth of 273 degrees. And last over here, we have the borehole deviation. Most boreholes that you have are not actually perfectly straight. This one's actually fairly good at a degree or less of deviation. Often it's well over a degree of deviation of the borehole.
Deviation from vertical. It's how far off vertical it is.
Yeah, and that plays into some of the processes that we apply to these to correct these features to make sure that this is the actual orientations. We correct for the deviation of the borehole to make sure we're getting the feature oriented towards properly vertical. All right, so next we're going to talk about the last format that we present in Princeton Geoscience logging reports, which is the structure plots, is what we call it. So what we're looking at here is 2 different sets of stereo nets, as well as a rose plot. And a rose plot here, which is just basically a 360-degree oriented histogram showing the direction of the dip of fractures. And for the stereo nets, Jim, do you want to remind everybody what a stereo net is?
You have to envision this round diagram here as a bowl. In this case, as they say, it says lower. That means it's a lower projection. And it's a bowl that has planes intersecting it. And what line they trace on the bottom of that bowl. In this case, you could probably imagine it, then that those beds are meant to be dipping in this direction. So the bedding traces are these arcs. There is what are referred to as poles to bedding. And so that's, any plane has a pole. It's 90 degrees to the plane. And in this case, these planes which dip off to the northwest like that have a pole that goes through them at 90 degrees. and it also goes down and intersects the bottom of that bowl. And so you're meant to be looking at where that pole would intersect the bottom of the bowl and then trace back up to the the image that you're looking at. The poles cluster at around 10 degrees. These circles are the contour dip. A pole plotting all the way out here would be for a vertically dipping fracture. One plotting exactly at the center would be for a horizontal fracture. And as you go progressively out, you're getting to steeper dips. So anyway, that's what that basically shows.
And inversely, I'll point out that if the bed lines were closer to the middle, those are more steeply dipping fractures.
Okay. Tim, what do these particular stereo nets show?
Yeah, so here are the stereo nets that we present here. So first, on the left, we have a stereo net of the direct observations of bedding that we showed on those previous structure plots here. So these are the actual grain size or color changes that we saw and called as direct observations of bedding. And then up here, we have our complete set of fracture populations. So we have, using, again, our classifications for minor open fractures, partially open, major open fractures, or filled fractures. And different log analysts have different classification systems, which gets into different presentation formats that people can use, which Jim will talk about here.
Right. Yeah, that's true with all of these logs. Different logging contractors have the opportunity to present the data different ways. Many of them are in common. It's just certain, on most of the logs, it's certain tracks. Like a gamma log looks like a gamma log, depending on what the scale you put it at. But in this case, Princeton Geoscience's format, especially for Newark Basin sedimentary basin rocks, where it's a dipping, leaking multi-unit aquifer system, where the bedding fractures are really important in terms of the contaminant transport. Many of our site investigation clients have expressed an interest in knowing more, a better idea about what the bedding orientation is from these things, and having that shown on stereo nets. So we've decided to call out bedding fractures from the larger population of fractures for a couple reasons. One being that the mean value of all fractures here, it's kind of meaningless. It's like, 9.5 degrees towards 305. In a sec, you'll see that the dip is off significantly from where, if you call out just the bedding fractures.
This mean is taking the mean of all of these low angle fractures as well as these high angle fractures, which is why it's meaningless as a complete set mean.
And so the other reason there's a desire to pull out that subpopulation of fractures is sometimes on some sites you don't have visually evident bedding in the optical televiewer log. Maybe it's a short log, or maybe it is rather featureless red mudstone, and it's not possible to pick anything out. But you would want to at least pick out the bedding fractures and to give yourself some idea of the structure of that, that bedding oriented features that are so important in a leaky multi-unit aquifer system. And Tim, what's the method we use to go about that?
Yeah, so to get these bedding oriented fractures we plot on this lower stereo net, ideally we'll have a good set of direct observations of bedding, and we'll use that. But when lacking that, we'll use map information or other site information, outcrop measurements, other things that people have for their sites. And from any one of those average orientations, ideally, again, the one we've directly observed, we'll take a bounding set. We'll query the total set of fractures around a bounding set of a range of strike and dip. So, strike within a few degrees and dip within a few degrees to get these bedding-oriented fractures. And looking at these bedding-oriented fractures on this stereo net here, we see, getting back to why they're so important, as Jim pointed out, see we have both of the minor open fractures and one of the major open fractures within this population set. And we have 32 of the total 81 fractures in this well are bedding-oriented. So most of the fractures are bedding-oriented, and some of the more major ones are bedding-oriented. And from this, we get our mean, and this mean here of 10.3 degrees towards 306 degrees is very close in agreement to the direct observations of bedding, which were also 10.3 degrees towards 308 degrees. So we're dead on with the dip magnitude and within less than 2.5 degrees of azimuth.
Another thing we can do in reports is combine the two sets of bedding indicators effectively. You have the direct evidence of bedding, based on the optical log and contacts that are readily obvious, and then the bedding fractures. And together, you get a population of fractures, which is even of features, which is larger and increases your overall accuracy if you're looking at a mean value. And what we found, we became curious about this because the standard in New Jersey for understanding structure within this leaky multi-unit aquifer system has been the drilling of at least 3 deep test holes and correlating the logs with a natural gamma log. That's an expensive prospect and not always something that people want to do as the first step, particularly at maybe a smaller site where you wouldn't even expect a very large plume, gas station type of scenario. So we were curious to know how well nicely constrained structural data like this from a single borehole would agree with on sites where we have that correlation. We've done the site-wide. And as we can explain in an additional video, it's the general finding is when you have nicely correlated gamma logs and have that, and you have decent data like this, like a good data set like this, it's been very close. I wouldn't say that the gold standard of log correlation and the 3-point problem is gone, but I would certainly say we have really strong indicative understanding of structure even from a single hole that's penetrated, say, 40 or 50 feet of rock, maybe a little more than that. Well, thanks for watching this presentation. We hope that it has been useful.
And please contact us if you have any questions, comments, or for more information.